This is the geometric meaning of what is called as gradient. So now let's start with a theorem. The theorem states like this. All right. So if phi of x comma y comma z, right? If this is a scalar function, if this is a scalar function, CGION, right, then the grad phi, okay, this is a vector. This is a vector normal to the surface, that is phi of x comma y comma z is equal to c. So this is the theorem. The theorem states that if at all you have a phi as a scalar function, then if you take a grad phi, that will be a vector normal to the given surface. We need to prove this now. All right. So this is the proof. So we'll start with the statement that let there be a vector r is a position vector. It's a position vector of a point. Okay, the point is denoted by p x comma y comma z, right? And this point is assumed to be present on the given surface. Okay, so on the given surface. So what is that given surface? Is phi itself. Phi of x comma y comma z is equal to c. Okay, so this is the given surface, and basically we are trying to find out, right, whether we can represent the normal to that surface. Okay, then we know that if that is the case, the vector r can be represented as x of t into I cap plus y of t into j cap. All right, plus the last one, that is z of t into k cap. Right, now let's try to find out the dr by dt. This implies dr over dt is nothing but this is dx by dt into I cap plus dy by dt into j cap plus this is dz by dt into k cap. Right, this is, what is this? This is a tangent to the surface, is tangent to the surface at the given point P. So they have given a point P, and we could find that, right, this is the specific value of the tangent, right? So also let's do the del phi. So what is this del phi? Del phi is nothing but this is dou phi by dou t into I cap plus this is dou phi by dou, my mistake, this is x, sorry. We know that this is just a second. All right, so this is nothing but, so this is dou phi by dou x into I cap, dou phi by dou y into j cap plus dou phi by dou z into k cap. Okay, so this means let us try to take the dot product of these two, right? So let me call this is equation 1. Let me call the equation number 2. Anyway, I know that both are vectors. So when you have the vectors present, you can definitely take the dot product, right? So then I'm going to take the dot product of del phi dot, this is dr by dt. Okay, so when I'm writing like this, so this means this is equal to, let's write the del phi first. This is dou phi by dou x into I cap, dou phi by dou y into j cap. This is dou phi by dou z into k cap. This is the first function dot the second function. So second function is dr by dt. So this is dx by dt into I cap plus this is dy by dt into j cap. This is dy by dt into j cap plus dz by dt into k cap. Both I'm trying to take a dot product. So dot product is nothing but x are the coefficients of I you can multiply. So this becomes dou phi by dou phi by dou x into this is dx by dt plus second term, this is dou phi by dou y into dy by dt plus this is dou phi by dou z into dz by dt. Okay, so now let us consider what is this. Let's hold on to this. Okay, this is equation number 3, right? Now what we do, we consider the phi of x comma y comma z is equal to c. This is the given surface. Okay, so where we know something, that is there is x is given by x of t. X is a function of time, so y is also a function, this is y of t. At the same time the z is also z of t. Okay, and c is actually a it's a constant. Sorry, my mistake. A-N-E-T. Okay, this is a constant. All right. In this particular situation, let's try to analyze this so that let's differentiate. Since this given function is a constant, phi of x comma y comma z is equal to constant, right? If we differentiate both sides. So when we differentiate both sides with respect to t, okay, with respect to t, so I get on the left hand side this is d phi by dt, right hand side becomes equal to 0. Okay, so this is d phi by dt is equal to 0. Now I understand that what is d phi by dt. D phi by dt, right? Because phi is a function of x and x is a function of time, I have to perform the differentiation only using one technique, that is called as using total derivatives. That's actually a concept from differentiation. Okay, so by using the concept of total derivative, right, we can write the d phi by dt as, it's a partial derivative. First it comes a partial, this is dou phi by dou x. This is just because phi is a function of x, into x could be differentiated, right? For x we can definitely differentiate with respect to time, so that is dx by dt, plus similarly the whole function is made up of y as well, so I can write this is dou phi by dou y into this is dy by dt, total differentiation with respect to of the function phi with respect to t in terms of y. Same, this is dou phi by dou z into this is dz by dt. This is the left hand side, right hand side is already given 0, so let's call this as equation number 4. So now what I want to do, I will go back, I will check the equation number 3, right? Equation number 3 and equation number 4 are same, right? So 3 is equal to 4. So when I say equation 3 becomes equal to equation 4, so equation number 3 is equal to equation number 4 implies left hand side of equation number 3 is the product, that is del phi dot product of the dr by dt, and the right hand side of equation 4 is equal to 0, right? So the dot product equal to 0, this implies the del phi and the dr by dt are, right, mutually perpendicular, right? So now I know that this is a tangent to the surface, so this has to be the normal, that's all. So since the dr by dt is the tangent to the given surface, right, the other one which is perpendicular to the tangent should be what? Should be the normal, that's all. Okay, so that's the concept using which we are defining now. So since the dr by dt is tangential to the surface, this implies the del phi is the normal. Okay, this is the normal to the surface. So very simple and very straightforward. Any surface is given, right? You will simply find out the normal to the given surface by performing del phi. All right, that's the first thing, right? Then after this we actually have another function that is coming up, another theorem. So let's try to give a theorem statement now. This concept is what is called as the directional derivative. It's called as directional derivative, right? Let's try to define the directional derivative now. So that is, if let's assume that there is a phi given x comma y comma z, right, is a scalar function, is a scalar function, and let's assume that there is a vector d given. All right, so and the vector d is a given direction, right? D is a given direction, any direction which is given, right? Then the del phi dot n cap, where how do you find this n cap? N cap is the unit vector along the direction of d. So d divided by magnitude of d, right, is the directional derivative, right, of the phi. All right, this is along this d. So along this d, what is the directional derivative? Which means I need to find that whatever vector is given, first you find its unit vector. For a given phi, you find del phi, right? Use this to calculate the dot product del phi dot n cap, which is nothing but the directional derivative. Okay, but with respect to what is called as the directional derivative, we have a theorem coming up. Okay, so Theorem. All right, this is a theorem. The directional derivative of a scalar function of a scalar function. So the scalar function is say phi, okay, at any point, at any given point, is maximum right? It's along the del phi, right? It's obvious, we already know the why the reason is, right? Because it's a dot product. Dot product is maximum if you find the dot product of two vectors which are in the same direction, then you can say that it is maximum. We know that. Anyway, we'll prove this. So in order to start giving a proof of this, let's start with the definition, right? So we know that, right, the del phi dot n cap is the directional, it's a directional derivative of the given phi along n cap. So this is what we know now. So what we try to do, so this implies the del phi dot n cap is nothing but, this is magnitude of del phi, first vector, into magnitude of n cap, right, into the cos of the angle between the del phi and n cap, right? So this is the equation where the theta is what? Theta is angle between the del phi and n cap. Now you see that cos theta is the one, so magnitude of del phi is some magnitude value, magnitude of n cap is 1, right? So since magnitude of n cap equal to 1, So this is del phi dot n cap is nothing but magnitude of magnitude of del phi into 1 into cos theta. So magnitude of del phi is a fixed value, but depending upon what is the value of cos theta, right, the directional derivative is going to change now, right? So I know that when cos theta is maximum, cos theta is 1 only if theta is equal to 0, correct? So cos theta equal to 1 if theta equal to 0. So what do you mean by theta equal to 0, right? This implies the del phi, this is coincides with n cap, right? So this means what? When they coincide with n cap, this implies the del phi is along n cap, then only this is maximum. Okay, so we proved the second theorem as well. Okay, now let's go to the next concept in this. The next concept is, this is tangent plane and a normal line. So we are supposed to find some equations now. Okay, now so this is the concept. So if let us say the phi, which is equal to or phi is equal to phi of x comma y comma z equal to a constant. Okay, b the equation of a surface. Okay, it's a surface, and let us say p, which is x1 comma y1 comma z1, is it's a point. Okay, it's a point on this particular surface. So on I can say on it is a point on it, right? This implies, now under this condition you have a surface and you know one point right above this. So if this is the case, we know now the equation of tangent, then the equation of tangent plane at P is, so if you want to find a tangent plane, this will be it will be of the following type. Okay, that is capital A into x minus x1 plus b into, this is y minus y1 plus c into z minus z1. Okay, equals to 0. This is called as a tangent plane, right? And also we have another equation which we will write. This is equation of what is called as a normal line. Okay, this can be written like, this is x minus x1 by a which is equal to y minus y1 by b equal to, this is z minus z1 divided by c. Okay, so where we are supposed to write the values of a, b and c now. Okay, so where, what is a? So this a can be easily found. You differentiate dou phi by, find dou phi by dou x and substitute the value, that is, you know that the value of x1 comma y1 comma z1, that simply gives you the required value of a. Okay, similarly the b can be found by using the dou phi by dou y at the same point, that is x1 comma y1 comma z1. Similarly c is equal to, this is dou phi by dou z x1 y1 z1. Okay, now all right, let's, similarly this was all about the del phi. Okay, gradient, we saw what is a gradient. Now we'll go ahead and we'll look at what is called as the divergence. What happens, what exactly is divergence? So here we are going to look at the physical meaning of what is called as the divergence. So we know that there is the second operation that is possible on a vector is divergence. Okay, and divergence will be applied to what? Applied to a vector. So if, let us say, vector v is in terms of x comma y comma z, is a physical quantity. If at all this is a physical quantity, then the divergence of this vector v, right, always gives the rate at which that physical quantity is originating. Okay, at that given point. So at, I can say, at that point per unit volume. So for a given particular quantity v, right, how much, right, it is varying at that given point, right? We can relate it in this fashion. Okay, now we have a specific condition here. What if this del phi divergence is equal to 0? Okay, so if divergence of v vector is equal to 0, this means, you see that, right, the total gain of this particular vector at that particular point is 0, right? It's not changing at all, right? This implies, if this is the case, you call it as the vector v is, it's called as solenoidal vector. It's a solenoidal, solenoidal vector. So I need to remember this one thing. So if at all I see that a vector which is like this, right? If somebody asks you to show that this particular vector is solenoidal, what you are supposed to do, you simply take a divergence of that vector and show that it is equal to 0. So using this you can say that the given vector is a solenoidal vector. So this is the physical meaning of a divergence. Similar to the divergence, we also have what is called as the curl. All right. So now quickly let's look at the physical. Sorry, just a second. Okay. The next concept is physical. Physical meaning of curl. So curl means it is actually a rotational, right? So now when you actually apply the curl, what you get is called as the rotation, right? Because of the curl of, or because of the effects of a vector, how much rotation you can obtain from that, right? What is the effect of the given quantity when you take a curl is how much rotation you can obtain from that. Okay, so if you say that, let's start like this. If v, which is a vector of x comma y comma z, right? If vector say is a vector quantity, and let us say curl, this is curl of vector v is 0, this implies, right, this particular vector v is irrotational, IRRO, irrotational, in the sense it will not rotate. All right, so if you consider something like maybe a velocity and angular velocity of rotation, when you take a cross product, you see that the answer comes to be equal to 0. This is what we know in physics, right? The same thing can be applied to understand these concepts. Okay, all right, so let's start with the problems of this. So the first question is like this. Find the unit vector normal to the following surfaces. All right, so the first one is x square y plus 2xz equal to 4 is a surface at a point 2 comma minus 2 comma 3. So now my intention is that I have to find out what is the unit vector that is actually is perpendicular at a given point. Okay, right. Now, so we will start with phi, assigning phi. Phi is equal to, this is x square y plus 2xz. Okay, so our intention is to find del phi first. So what is del phi? Del phi is nothing but, we know this is dou phi by dou x into I cap plus dou phi by dou y into j cap plus dou phi by dou z into k cap. We just have to find this. Okay, so substitute. This is equal to, this is dou by dou x of x square y plus 2xz into I cap plus this is dou by dou y of x square y plus 2xz into j cap plus this is dou by dou z of x square y plus 2xz into k cap. So differentiate now. So dou by dou x, the function is getting differentiated with respect to x. So this is 2xy plus 2z into I cap is the first term. Then I can see that the second function is with respect to y. So y will vanish. So after that I have left with x square into j cap plus, right, the last term is with respect to z. So this is 2x times k cap. This is what is the del phi. Right, so del phi is nothing but it's the normal vector, but I want the normal vector at the given point. So del phi, right, at the given point, that is 2 comma minus 2 comma 3 is nothing but, we will substitute the same thing. Okay, so 2 into minus 2 plus 2 into 3 times I cap plus this is x square, so 2 square into j cap plus this is 2 into 2 k cap. So you can see that this is 8 minus 8 plus 6 is minus 2 I cap. This is plus 4 j cap plus 4 k cap. This is nothing but the required normal vector. But what they have asked is, therefore the unit normal vector, right? This, let's denote it as n cap, which is nothing but the del phi divided by magnitude of del phi. So we need to calculate the same thing now. So let's do that. This is equal to, so let's write this. This is minus 2 I cap plus 4 j cap plus 4 k cap divided by square root of this 2 square plus 4 square plus a 4 square. So this is equal to minus 2 I cap plus 4 j cap plus 4 k cap whole divided by root of 2 square is 4 plus 16 plus 16. So this is minus 2 I cap plus 4 j cap plus 4 k cap divided by root of 36. So it's a perfect square, so you can see that this is 6. Alright, so this is 1 by 6 into minus 2 I cap plus 4 j cap plus 4 into k cap. So under this situation, now we can write this as, so 2 will cancel with this. This is minus 1 by 3 I cap plus 2 by 3 plus 2 by 3 k cap. This is the required unit vector normal to the given direction. Alright, so this is the simple solution. The next problem is we change the surface now. So phi is equal to x into y cube into z square minus 4. And let's say at the given point minus 1 comma minus 1 comma 2. In this case, the first step is to calculate the del phi. Gradient of this phi is nothing but from the basic of this dou phi by dou x into I cap plus dou phi by dou y into j cap plus dou phi by dou z into k cap. So we will substitute the given phi now to this. So this is equal to the dou by dou x of the phi, which is x y cube z square minus 4 into I cap plus the same differentiation but now with respect to y. So this is x y cube z square minus 4 into j cap. Alright, plus the last one, that is dou by dou z of x into y cube into z square minus 4 times k cap. So this answer now, as you can see, x, it's happening with respect to x, so this is y cube into z square I cap. Alright, the next term, there happens differentiation with respect to y. So this is 3x into y square into z square times j cap plus last one. You can see that differentiation happens with respect to z. So z square becomes 2z. So 2 into x into y cube into z. Alright, times k cap. This is nothing but the del phi, gradient of the given phi. Now I want this gradient to be found at a given specific point, correct? So now we'll apply that. So that del phi at the given point. So we'll calculate that first. Okay, del phi at which point? This is minus 1 comma minus 1 comma 2. So this is minus 1 cube is minus 1 into z square. So minus of this is minus 1 into, I'll write the answer directly, just verify. Okay, so this is y square, y cube, so minus 1 cube is minus 1 into, so z square, 2 square, which is 4 times I, plus this is 3 into minus 1 into minus 1 square is plus 1 plus z square equal to 4 times j cap plus 2 into minus 1 into y cube is also minus 1, z is 2 times k cap. So this answer comes to be minus 4 I cap, 3 to 4, so plus 12 j cap and plus 4 into k cap. This is del phi. Okay, now what I am supposed to do, I am supposed to calculate the unit vector. n cap is equal to the del phi divided by magnitude of del phi. So del phi is nothing but minus 4 I cap plus 12 j cap plus 4 into k cap, whole thing divided by under root. So squaring the terms, 4 square is 16, 12 square is 144 plus 16. Okay, so now this means I can take a 4 common in the numerator, right? This is let me take a minus 4 outside. What happens when the minus 4 goes out? This is I plus 3j let me just verify. Sorry, I made a mistake here. See, this is not positive, this is negative. Just make a correction if you have noted it wrong. So this is minus. So when that is minus, I think, yeah, this is also minus. Okay, so now when minus 4 goes out, so I am expecting this also to be minus. Okay, minus has gone out, so what remains is a plus. So I plus, this is I cap 3j cap minus k cap whole divided by, so when I take 16 outside, 16 becomes a 4, alright, into root of 16 is gone out. This is 1 plus 9 plus 1, 9, 10, 11. So 4 gets cancelled. So this is minus 1 by 11 times, this is I plus 3j minus k. This is the required unit vector.